One of the most striking features of the transition elements is their ability to exhibit several oxidation states in their compounds. This unique ability is due to the small difference in energy between the Ns and N-1d orbitals. Because of this, in addition to Ns electrons, N-1d electrons also participate in bonding. The table here lists the common oxidation states exhibited by the first row transition elements. Note that the oxidation states shown in brackets correspond to unstable oxidation states. Some points may be noted from the table. Except for scandium and zinc, all the other elements show more than one oxidation state. Scandium, due to the availability of very few electrons for bonding, does not show variable oxidation states. On the other hand, zinc, due to the presence of too many d electrons, has fewer orbitals available for bonding, and thus does not exhibit variable oxidation states. The elements from titanium to zinc, with the exception of copper, show a minimum oxidation state of +2. Copper shows a minimum oxidation state of +1. The maximum oxidation state is given by the sum of the s and d electrons for the first 5 elements. For example, scandium, titanium, vanadium, chromium and manganese exhibit maximum oxidation states of +3, +4, +5, +6 and +7 in the form of their oxides, oxyanions and oxycations, as shown here. The maximum oxidation states of the elements after manganese are not at all related to their electronic configurations. For example, cobalt shows only +2 and +3 stable oxidation states. The relative stabilities of various oxidation states of 3D series elements can be correlated with the extra stability of 3D0, 3D5 and 3D10 configurations to some extent. Thus, a titanium 4+ ion with 3D0 configuration is more stable than a titanium 3+ ion with 3D1 configuration. Similarly, a manganese 2+ ion with 3D5 configuration is more stable than a manganese 4+ ion with 3D3 configuration. The transition elements exhibit oxidation states that differ from each other only by 1 unit. This is in marked contrast to the S-block elements, which exhibit only the group valency, and the p-block elements, which exhibit either the maximum group valency or a valency less by 2 units. For example, manganese exhibits all the oxidation states from +2 to +7, which differ from each other by unity. On the other hand, tin and lead, which belong to group 14, exhibit oxidation states of 2 and 4. You know that in p-block elements, lower oxidation states are favored by heavier elements because of the inert pair effect. But in d-block elements, higher oxidation states are more stable for heavier elements. For example, in group 6, molybdenum 6, tungsten-6 in the form of their oxyanions are found to be more stable than a dichromate ion, in which chromium is in its highest oxidation state of 6. Thus, a dichromate ion acts as a strong oxidizing agent in an acidic medium, while the oxyanions of molybdenum and tungsten do not. Some transition metals also show zero oxidation states in complexes like carbonyls, where the ligand acts as a pi acceptor. Nickel tetracarbonyl and iron pentacarbonyl, shown here, are two examples of a transition metal in zero oxidation state. In their lower oxidizing states, these elements form ionic compounds. For example, manganese-2 oxide and chromium-2 oxide are ionic in nature. The tendency to form ionic compounds decreases with an increase in the oxidation number of the metal. Higher oxidation states give rise to covalent compounds. For example, manganese-2 oxide is ionic. Manganese-4 oxide is intermediate between ionic and covalent. And manganese-7 oxide is purely covalent. As the oxidation state of the transition metal increases, the charge density on the metal also increases. This results in an increase in the polarization of the anion charge cloud by the metal, and hence, the covalent character increases. The acidic nature of the oxides increases with an increase in the oxidation state of the transition element. For example, manganese-2 oxide is basic. Manganese-4 oxide is amphoteric, while manganese-7 oxide is acidic in nature. Similarly, chromium-2 oxide is basic, chromium-3 oxide is amphoteric, and chromium-6 oxide is acidic. A gradual change in nature of the oxides from basic to amphoteric can be clearly seen in vanadium. Vanadium-3 oxide is basic, while vanadium-4 oxide is less basic. On the other hand, vanadium-5 oxide is amphoteric with more acidic properties. Vanadium-5 oxide reacts with alkalis to give orthovanadiate ions, and with acids to give dioxovanadium-5 ions. In higher oxides, the acidic character is predominant. Thus, manganese-7 oxide gives permanganic acid, while chromium-6 oxide gives chromic acid and dichromic acid.